So when
There's Akshay. We will
click
get
the button, start the webinar.
Yeah, in just 1 minute. I just want to say, Akshay, this is Hua-Jung. I started a Slack thread with us on the QxQ Slack, so we can do things just like normal, and we'll take a break halfway through and do questions after.
Sounds good. Nice to meet you, Hua-Jung.
Nice to meet you.
Akshay is amazing, and we'll answer questions all throughout.
Well, thank you.
Perfect. All right, everyone ready?
Yeah.
Awesome. Let's do it. Good afternoon, everyone. Actually, Gabby, if you want to open the chat and let's have everyone give Hua-Jung a really warm welcome. We have a special guest lecture today. Let Hua-Jung know where you're joining from. It's a special guest lecture. We have Hua-Jung, who is from the IBM Quantum Education team, who will introduce herself even more in just a few minutes. But it's a really special day, and we're excited to have her here. So thanks for giving her the warm welcome. Folks, if you have not yet, we provided several announcements on Canvas asking you to do this, but please make sure you've downloaded the notebook from Canvas, the Jupyter Notebook, and upload that to your IBM Quantum Experience account. Hua-Jung will be walking you through that notebook as part of her lecture today, so you can practice learning as she introduces the new content. If you cannot, don't worry about it. You'll be able to follow along based on what you can see. But if you're able to, we'd like you to practice as we go. I have just a few quick announcements before I turn it over to Hua-Jung for the rest of the lecture. So if you have not already signed up, Gabby, if you wouldn't mind flipping the slide. If you haven't signed up already, a week from yesterday, next Saturday, is our first ever Diversity in Quantum Computing Conference. So this is a pretty incredible event. We're really excited about it. It will run all day. So if you have Saturday labs, it's okay. Just join us when you're not in your lab section, but we will have incredible IBMers like Hua-Jung who will be speaking about their experiences. We'll have policymakers like the leaders of quantum education at the National Science Foundation in the US. We will have graduate students talking about their personal journeys in quantum computing, finding jobs, pursuing educational programs, and we'll have faculty from MIT, Howard, Harvard universities, all to share their experiences, their lessons learned, to inspire all of us for what we can do to ensure that the future of quantum computing is diverse and inclusive for all of us. Stay tuned also for some information about a potential extra credit opportunity for students who attend that event. And then just two other quick announcements other than the diversity conference. This week, you will again work with Jupyter Notebooks during your lab sections with your teaching assistant. So that will be posted on Canvas tomorrow. Please download that in advance of your lab. Otherwise, there's the chance, like some of you have seen before, that Canvas could crash if everyone tries to download it at the same time. So please download it in advance. Your TAs will kick off right away and would like you to be prepared with those pulled up already. And just lastly, we're going to get into QxQ today. Lab and homework for the rest of the week will be a review of everything you've learned. So if this is new for you and you're feeling a little bit overwhelmed, there will be plenty of opportunities to practice. And at the end, Hua-Jung will tell you just a little bit more about a really incredible IBM program called the QxQ Advocates, and an opportunity to get more involved with QxQ. Cool. I think that's it for me. And then Hua-Jung will take it away for the next 2 hours of our lecture.
Okay. Hi, everybody. I'm Hua-Jung. I'm from IBM Quantum. And my job in my team is making educational material for quantum computing using QxQ. And I started working from last year, June, so it hasn't been a year yet. And I recently made, I don't know if everybody knows a QxQ textbook. If you go to QxQ textbook, there's a chapter 7, which has 7 labs. That's what I made, and then it got merged recently. So I think that's enough for me. So I'm gonna start. Doing today's lecture. So hopefully everybody can see my screen slide. Okay. So before we start learning how to use QuizKit, I'm gonna go through several basic concepts. In quantum computing, a basic unit of information is called a qubit, while a basic information unit in classical computer is called which is called a bit, has 2 discrete states, 0 and 1, and it's processed by logic gate. State of a qubit is a normalized vector in 2-dimensional complex vector space. So the number of the states of a qubit, number of qubit state is infinite, as there are infinite many vectors in 2-dimensional complex space. The state of a qubit is transformed through unitary operation, also called quantum gates. So here, the figures describe what I just talked about, state of a qubit being a normalized vector in 2-dimensional complex vector space, being a complex vector. So first, let's consider just a normal vector in 2-dimensional real valued space, which is familiar to us. And as we know, any vector can be represented as a linear combination of 2 bases, unit x and unit y, with appropriate coefficients. Also can be represented as a 2-dimensional column vector. In the same way, 2-dimensional complex vector, in the same way, state of a qubit can be represented in this way, which is a 2-dimensional complex vector. 2-dimensional complex space illustrated, which is illustrated as a block sphere here, looks a bit different from 2-dimensional real valued space, but since it's 2-dimensional, so there are 2 basis vectors, which are 0 and 1 on the z-axis of the block sphere. Then any 2-dimensional complex vector can be represented as a linear combination of these 2 basis vectors, 0 and 1. Here, the purple vector is an example of a state of a qubit, which is a psi in the mathematical expression. And since, as we learned from the previous slide, state of a qubit is a normalized vector. So the size of this vector, the size of the psi, should be 1, which we can check through this component. So the 2 basis vector we just saw, corresponding to the 0 and 1 state of a classical bit, is called computational basis. Why they are so special will be more clear when we talk about measurement. So now 0 and 1 are not binary integer, but they are a vector. So for a qubit, 0 and 1, we represent the 0 and 1 state as a shorthand cat notation, as is shown here, and also can be represented as a 2-dimensional column vector. Then the general state of a qubit, any qubit state can be represented as a linear combination of 0 and 1 with complex value coefficient that satisfies normalization condition. Then one of the most important property of a qubit called the superposition, meaning that a qubit can be in not only 0 or 1, but both at the same time, is nothing but this superposition. So here the figure shows the state for classical bit and qubit. So if you see the top left figure, these 2 vectors shows the 2 states that classical bit can have. So there are only 2 states for the classical bit. But for a qubit, as the figure in the bottom right side block sphere shows, there are infinitely many states. Basically, any vector in the block sphere with a length 1 can be qubit state. So now let's say we want to encode information on a qubit. So as we learned now that we can encode 0 or 1 or both at the same time. Initially, qubit is always prepared in 0 state. So if we want to encode 0, we don't have to do anything. But for any other state, we need to apply a proper quantum gate or unitary operation. Just like we need to apply logic gate on a classical bit to change its state. Such instruction can be made by building quantum circuit, which is shown as a diagram combination of this wire and box. That's a quantum circuit. And this quantum circuit is what we execute on a quantum system, quantum computer, for a desired computation.
Hey, Huajong, would you mind using your mouse just to hover over the part you're talking about to help us follow these slides just a little
That's
bit?
what I want to do, but it doesn't really do it. It doesn't really do it. Oh, let me see. I don't think it, my mouse is not, I cannot do it.
Okay.
I'm
Okay.
sorry. Oh, is it follow? Am I going too fast?
Nope, not too fast. I think good.
Okay. So again, as I said, qubit state is a vector. So how we manipulate the information, how we manipulate qubit state, it's very similar to how we perform operation on a real vector. But among all the operations that can be done on a real vector, only the rotation-like operation is allowed for qubit state. Since qubit state is a complex vector, the rotation in complex valued space is called unitary operation, which shares similar property of normal rotation, linearity, reversibility, and preserves the logical relation between the states. So what does the preserving logical relation between states mean? So if you think about two vectors in two-dimensional real space, and let's say they are orthogonal to each other, then they will remain orthogonal after they are transformed through the rotation. If they were parallel at first, then they will remain parallel to each other after the rotation. Basically, rotation preserves the angle between the any two vectors. So in math, we can summarize that property as preserving the inner product of this two vector. So let's see, for example, for complex vector, the qubit state psi and phi, two qubit state psi and phi, and let's say they are orthogonal to each other. Then after we transform by unitary operation, quantum gate, they transformed to u psi and u phi as shown in the bottom of the slide. Then u psi and u phi are also orthogonal to each other because unitary operation quantum gate has this same property as rotation. So basically, the inner product of psi phi is the same as inner product of u psi and u phi. If psi and phi are same vector, so if you replace in the equation, replace the phi with the psi, then what it implies is length preserving. So we kept saying qubit state is a normalized vector. Then because of this property, even after we apply quantum gate on the qubit, the state of the qubit is still normalized. So here I show some examples of single qubit gate, single qubit gate. Those diagrams are quantum circuit, as I said. The wire corresponds to a qubit, box is for a gate, and time flows left to right. Here I'm showing two very important single qubit gate, X gate and Hadamard. X gate is the same as a NOT gate in classical circuit, and Hadamard transforms basis state to uniform superposition state. So if you see the top figure, circuit with the X gate, so when X gate applies to 0 state, just like a NOT gate in the classical circuit, it produces output state 1 and vice versa. If Hadamard applies to 0 state, then it transforms the state to normalized 1, 1 in the column vector notation. You see 1, 1, and then the coefficient in front of it is the normalization vector. We call this a state plus a state. If we apply Hadamard on the state 1, then the transformed state will be in the minus state, which is normalized 1 minus 1. Here I show how each gate works on each basis, because qubit state is a vector, and as I said, quantum gate is a linear operation. So if we know how the gate works on each basis, then we can figure out, we know that how each gate works on any general state. So here the figure shows, figure describes Xn Hadamard gate in block sphere. So if you see top right figure, smaller block sphere figure, it describes, so every gate is a rotation, as I said. So X gate is pi rotation around the x-axis described in the top right figure, smaller one. And through this operation, if you see the top left figure, the gray vector goes to purple vector goes to 0. Purple vector goes to gray. So 0 goes to 1, 1 goes to 0. For Hadamard, the Hadamard is a pi rotation around axis, some midway between x-axis and z-axis, as is shown in the bottom left figure. Another pi rotation around the axis, which is illustrated as a dotted line. Through this rotation, if you see the bottom right figure, purple vector transforms to gray, gray transforms to purple. So 0 goes to plus, plus goes to 0, 1 goes to plus, 1 goes to minus, and minus goes to 1. So let's think about how X gate work in general state, now that we know how it works on each basis. So top two circuit diagram shows how it works for each basis, which we already saw. And then bottom, the last figure is when the qubit state is in initially state psi with the coefficient alpha and beta, some general state, and then the X gate is operated on that qubit state. And as I said, this general state can be represented as a linear combination, alpha 0 plus beta 1. Then the X gate works on each basis in the linear fashion parallelly, so that it produces alpha 1 plus beta 0, because X transforms 0 to 1 and X transforms 1 to 0. Then you notice that X gate switches the position of the component in the column vector for the state of a qubit. We say that superposition is one of the resources where quantum computer gets its processing power. So what is so special about superposition? So if once the qubit is in the superposition state, like a plus state here, then the following operation is applied linear fashion on each basis parallelly, just like a parallel computation. So if X gate is applied, just like as shown in the bottom circuit, applied on the superposition state plus state, then the output state will contain parallelly computed result, since X applies a linear fashion linearly on the both state. So if you see it, the output states contain this parallelly computed output, which seems pretty powerful. However, there is a caveat. State of a qubit, quantum state, is not directly observable, as we learned from quantum physics. The information encoded in a qubit can be only obtained by measurement in the computational basis. The process of the measurement collapses a qubit state into either 0 or 1 with the probability determined by magnitude square of the coefficient. So the thing is, we do the computation on quantum state, but what we obtain as output are classical bit. That's why this is 0, 1 classical bit states are special and referred as a computational basis. So for example, let's see, we have a qubit which was initially in the 0 state, but then we we apply quantum gates for the computation that we want. So now qubit is in state, different state called psi here. So we want to know what is this result output state to get our computational result. If it's a classical bit, you just read it, what state 0 or 1 for a single classical bit. But for qubit, we have to measure it. So when we measure it, the state of the qubit will collapse to 0 or 1. That's what we will obtain. And with the probability determined by the size, square of the size, coefficient size here, alpha and beta square. So for example, if alpha is way bigger than beta, if size of the alpha is way bigger than beta, when you measure it, when you measure this state psi, you're gonna most likely get the output 0 as your output. Also, don't forget that once you measure the state, once you measure the qubit, the state of the qubit will be state of the qubit collapses to the measured state, this classical bit 0 or 1, not in the psi anymore. So here I show a specific example. So let's consider first a purple vector in the Bloch sphere, which is also a purple vector, purple state psi. So there is a state, qubit is in this state, which we don't know yet. So we measure it. Then what we get as an output is 0 or 1 with half and half probability. Since, as you see in the Bloch sphere, this purple vector is positioned exactly halfway between 0 and 1. Same logic is applied to the light blue vector. So for this state of a qubit, our measured state will be most likely 1, since this vector is positioned very close to the 1 state. And then, as I said, once you measure it, it's not in the psi state anymore. It's gonna be in the 0 or 1 that you just measured. So by preparing many copies of this same state, for example, here psi, you prepare many of them, and then you measure all of them, then you can produce a probability distribution of getting 0 or 1 state, which is determined by the magnitude square of this of the coefficients of the state. So after you after you get the parallelly computed output through the superposition, what you get is not this output which contains this parallelly computed result. So we need to be smart in the algorithm to exploit the power of a quantum computer. So now let's move on to let's do some hands-on example using QxQ to implement these two single qubit gates that we just learned. So first, let's see. What is QxQ? So QxQ is open source SDK software development kit for working with the quantum computer at the level of it's just a toolbox that we can use to program quantum computer, Air, Ignis, and Aqua. Terra is a collection of routine for building and optimizing circuit, executing on real quantum computer, and post-processing. Air is a high-performance simulating package. Ignis does a quantum experiment for noisy verification, validation, and mitigation. Aqua is collection of quantum applications and algorithm that utilize a circuit, quantum circuit. So
Can you tell us? Oh, I'm sorry. Can you tell us a little bit more just about what each of those mean for folks who those words are new to them?
Oh, so I heard that it's from the Greek word, and as far as I know, Terra is for the like ground.
But how about,
and then air?
Sorry, not those words, but like high performance simulators versus noise verification. Just help us understand like what each of these looks like differently.
So like we are gonna use today Terra and Air. So we are not gonna look into Ignis and Aqua. So Terra is like when you to compute using the quantum computer, as I said, what we execute on the quantum computer is a quantum circuit. So we have to build a quantum circuit, and that's where we use a Terra. So we use a Terra to build a quantum circuit and also execute this circuit on the whatever the quantum computer we pick. And then sometimes we wanna not sometimes. So that's a quantum running the executing the circuit on the we call it backend. Backend can be simulator or quantum computer. And air is when we want to simulate it instead of using a real quantum computer. That's when we use air. So we're gonna get the simulating thing from the air package. After we run everything, we get the result so we build the thing and then we execute the circuit on the quantum computer, we are gonna get the result, right? But I'm gonna talk about very at the end, this result is very noisy. So we use tools in the Ignis package to improve the result by doing sometimes error mitigation, for example. Aqua is more like an application toolbox. So there are a lot of different application, and like I don't know if people have heard about VQE, for example, iteration application, or you wanna use this quantum computer to compute some problem in finance, some kind of very applied area. And this Aqua collection has this function which is already pre-coded, so you can just pass the input. For example, for quantum chemistry, like appropriate input is the pre-made function. So it's a toolbox. So if you have some particular problem in your mind, especially if it's widely used, you can probably find a appropriate function from Aqua package. And instead of instead of like coded everything from the scratch by yourself using Terra and everything. Even the error mitigation is included in the function inside the Aqua. So
that was very helpful. Thank you.
You're welcome. So the usual workflow is first we build this quantum circuit that we are going to execute on a quantum computer. But then before we execute that on a real quantum computer, we simulate it using the simulator from air and check if the circuit works as it should. And then we execute that circuit on a real quantum computer and get the output. Simulating quantum system using classical computer has several advantages. You can simulate system perfectly and produce ideal answer. Also, it can go larger qubit counts than most of the publicly available hardware. But as the table shows, the system with more than 50 qubits is not possible to simulate. So once you start doing some computation with more than 50 qubits, then you cannot really check your answer, what kind of answer is expected as an ideal answer. And today, when we do hands-on example using QxQ, we're going to work in IBM Quantum Experience, IQx in short. The IBM Quantum Experience is a cloud-based platform for using quantum computers. You can program quantum computer using QxQ in a Jupyter Notebook environment, or execute circuits graphically using Circuit Composer. Since we are going to use QxQ today, we're going to work in the Jupyter Notebook environment. So I assume that everybody already registered IBM Quantum Experience. So let's go there and log in into your account.
They used Circuit Composer during labs last week too. So they should be familiar.
Well, today we're going to use QxQ. Okay. So go into log in your account. And then if you see the left side of the window, there's an icon called the Quantum Lab. So click it to open Jupyter Notebook. This part takes some time for loading. If it takes too long time, I recommend close the window and go to the IBM Quantum Experience again and do the same thing, then it works for some reason. Uh-oh. I guess probably there are many people are logging in. I guess that's why it probably takes a longer time than usual.
Do you want to just help us understand kind of what we're looking at on the IBM Quantum Experience interface while we wait for it to load?
Oh, it got loaded. Sorry. So we're gonna go through like a when we go through the step, you're gonna see what each tab includes and how we can use that. So finally got loaded and open the Jupyter Notebook. And I heard that some of you downloaded. If you didn't download it, it's a pretty simple code. So you can just follow along with the lecture. Because a lot of people are on the QX. Okay, so like Rachel said, while it's downloading it, I'm gonna go through each icon. So here, the first icon, which looks like a house, called the dashboard. And since we don't want to close the Jupyter Notebook window, so I'm gonna open this on the new tab. And here, what we use using the dashboard is if you see the right side of the window, you see the list of the quantum computer, IBM quantum, we say IBM quantum system, quantum computer, and it shows for example, how many qubits that particular device has and quantum volume, and then the Q information, how many jobs are submitted. And probably you don't see as many systems as I do, because those include more than just a publicly available system, because I'm an internal person. The second icon called the Systems and Simulator, I'm going to open in the new tab as well. Oh, now it's loaded. Okay, since the notebook is loaded, let's go through this first. So once you open the notebook, any new notebook, this first cell is pre-coded. This is to import all the tools that generally used to code using QxQ. So just run the cell by entering shift to return, so that we get all the tools that we need.
Can I just clarify something quickly, Hua-Jung? Some students keep mentioning that the file is locked. I think if you're talking about Canvas, the homework notebook is locked. You'll have access to that after the lecture, but you should be able to download the Canvas notebook that Hua-Jung will be walking through. So if that's confusing, it's homework versus lecture. You'll see you'll be working with many notebooks for the next few weeks. So just make sure to read how they're labeled.
Yeah, so if you cannot find your downloaded notebook, I will just recommend here I loaded this page by clicking this Quantum Lab icon, you open this page and then click this new notebook. Then it's going to create a new Jupyter notebook, and you can open that Jupyter notebook, and then you can start coding with me together, with the lecture together. And as I said, first cell is always pre-coded for you. And so run that cell first. And here are some list of terminology, which is useful for us to know in advance. As I said, AIR is a QxQ simulation package. Specific simulator or device is called a backend. Execute is a function taking quantum circuit, and the backend runs the circuit. By default, execute simulates 1024 realization of the circuit. So you can list the list of the backends that AIR has by running this command, air.backends parenthesis. Then it shows what kind of backends are in the AIR simulation package. And as you can see, there are 4 different simulator: chasm simulator, state vector simulator, unitary simulator, process simulator. Today, we are going to use just the chasm simulator to simulate a quantum computer to get the ideal quantum computer's result. So let's make some quantum circuit with 2 single qubit gate we just learned, X and Hadamard. So here is the matrix form of the X gate, and it shows how it works on 0 and how it works on each basis of 0 and 1 state. And X gate is its own inverse. So let's check it by building a circuit.
Can you zoom in a little bit just on your screen?
Oh yeah, sorry.
No problem.
Is it better?
Yeah, perfect.
Okay. So first, define the quantum circuit with the 2 arguments, with a number of a qubit and number of a classical bit. So we pass the number of a qubit and classical bit that we need. And here we are talking about single qubit. So we need just 1 qubit. The first one is the number of a qubit. And then we need 1 classical bit where we are gonna store the measured state value to. After you define the quantum circuit, now we have only 1, but later we have more than 1 qubit. Then there's an index of the qubit and classical bit. All the index starts from 0. So when we have only 1 qubit, 1 classical bit, this is a 0th qubit, 0th classical bit. Through the circuit method, we apply X gate on the 0th qubit. That's how you apply X gate. And then we need to measure it to get the to extract the information about this qubit state. Measure 0th qubit and then store the measured value on the 0th classical bit. Using the draw function, you can check the circuit that you built graphically. So whenever you build a circuit, whenever you do any computation with a qubit, as I said earlier, qubit is always prepared in a 0 state initially. And then you have to start applying qubit gate to prepare the qubit in whatever the state you want, or transform the information by applying another qubit gate, etc. And here, as you see the diagram, this Q wire corresponds to qubit, double wire corresponds to classical bit. And as the graphical notation said, measuring the 0th qubit and store the measured state value to the classical bit. Now we are gonna use chasm simulator as a backend and then execute this circuit on that backend. So define the backend variable by grabbing the chasm simulator backend through the get backend method. So give me this chasm simulator backend and then assign it. We passed the quantum circuit that we just built, which is stored in the variable QC. We pass that in the backend to the execute a function to run the circuit on this simulator backend. Also, I want to tell you that I said in the beginning, the number of shot, the parameter value called number of shot is setting as 1024 as a default value, which we can change. So if you want to know like about some function, put the mouse on that line, and if you click Shift to tab, and then tap one more time, holding the Shift button, then it shows all the parameter value and then brief description about this function, docstring. And among the parameter, there is something called shot. So I don't set the parameter, this parameter here because I'm using the default value, but you can change this number of shot higher or lower as you want it. So number of shot matches, number of shot is number of measurement of the circuit that you build. So number of shot for a simulator is corresponding to repeatedly executing the circuit on the hardware. So as I kept saying, as I said earlier, like once you measure it, it collapses to 0 or 1. So to get the probability distribution, you need to make a lot of kind of like a lot of circuit, copy of the circuit, and you keep measuring it for each circuit, and then you can make a probability distribution. So if
Hi, Hwajung, could I ask a few questions that some of the students are posting in the chat?
sure.
Yeah. So in the circuit that we defined, so some of the students wanted to know. So in that cell, what does the 1, 1 mean? If you could repeat that, and then what is the, so basically these numbers like QC.X0, what does the 0 mean there? And then QC.measure 0, 0. I think some of the students were a bit confused about the numbers.
Oh, sure. Okay. So let's go back to the this cell making the circuit. So this first argument is the number of qubit that we need to build the circuit that we want. So here we want to build a circuit with X gate, single qubit gate. So we didn't go any other system more than 1 qubit. We just are working on just 1 qubit system right now. So the number of qubit for us now is 1. So first argument of this quantum circuit function is 1, is a quantum number of qubit. And the second argument is a classical bit. As I said, you measure the qubit to know the information encoded in the qubit, and you measure it. What you get as an output is classical bit. So after you measure it, you store the measured value. For example, here it should be 0 or 1, only the 2 states. And then you measure that value into the classical bit. And since we are measuring 1 qubit, we need just 1 classical bit. So the first argument is 1 qubit, and 1 classical bit. And here, when you apply X gate, we want to know on what qubit we want to apply X gate. And since we have only 1 qubit, there's no other choice but 0th qubit. So 0 here is the index of a qubit. So as I said, all the index starts from 0. So this qubit, for us, just 1 qubit, the index of this qubit is 0th qubit. And here we have only 1 classical bit, it's 0th classical bit. So what it means is apply X gate on the 0th qubit. And then
the 0 there is the index of the qubit.
Yes.
Okay, yes. I see.
Yeah, index of the qubit. And here, so only except for the very top number, which is the number of a qubit, number of a classical bit, rest of the indexes, rest of the numbers are index. It's like for X index of the qubit, and measure. The first argument is the index of the qubit that we are measuring. And the second argument is the index of the classical bit register, index of the classical bit where we are gonna store the measured value at. So what it means is after applying the gate, after the operation, measure the 0th qubit. Again, this is the index. And then measure the value to the 0th classical bit. Is it a bit clearer?
Yeah, so the first So in the QC.measure, the first number is the qubit that is being measured, and the second number is the classical bit
Index.
that
Yeah.
the measure will go to.
Right.
Okay.
Yeah.
Okay. And then another question I'm seeing is about the diagram that we drew.
Mhm.
So students want to know what the Q and the C are, and like why are there those two lines next to the C? What is that? Is there any significance to that?
Oh, it's just a differentiation. So the Q corresponds to qubit. C corresponds to classical bit. So wire, like we represent qubit as a one wire, and classical bit, we represent classical bit as a two wire. So it's just differentiation graphically. Are we talking about qubit? Are we talking about classical bit? And as I kept saying, once you measure the qubit, then the qubit will collapse into the classical bit state. So whatever the qubit you measure, when you measure, what you're going to get is a classical bit value. For the single qubit case, it's going to be single classical bit value, which will be 0 or 1. So once you measure it, you can store that value to the classical bit. Does it make sense?
Yep. Thank you.
Yeah.
And I think another question that students had was about, so going back to the quantum circuit 1,1. So some of the students wanted to know, is there any case in which those two numbers will be different, or are they always the same?
Yeah, so we're not gonna cover that case today. So if you go a little more advanced stuff, then you are gonna be in the situation you make a circuit, and then with some number of qubit, but you don't want to measure all of them because some of them used as more like, it's called ancilla, used more like to be used as an extra place for the computation. So basically, there's a situation that you make a circuit with several number of qubit, but when you get the result of the computation, you don't want to measure all of them. In that case, you make a circuit with, for example, 4 qubit, but then you want to measure only 3 qubit. In that case, the number of qubit of the circuit, quantum number of qubit of the circuit would be 4, and then classical bit would be, number of classical bit would be 3. Does that make sense?
Yep, thank you. I think that's all the questions for now, but can I jump back in whenever there are more?
Sure.
Okay, thank you.
Thank you.
Hwajung, will you zoom in just a little bit more? Sorry.
It's okay, sorry. Better?
Yeah, maybe one more.
Okay.
Perfect. Now it's crystal clear. Thank you.
Good. So after we build the circuit, now we are ready to execute this circuit. As I said, we're gonna just use the simulator for now. So our backend, which are gonna run the circuit, is a simulator. And we get the simulator from the package called air through the method called get backend. So in the get backend method, we're asking, get me the QASM simulator and assign that in the variable backend. And now we use the execute function to run the circuit on that backend. So you pass the circuit that we made, which we call variable QC. So pass the circuit and then pass the backend in the execute function. After you run the circuit, you get the result through the result, which contains a lot of information. Among the information, what we need is just a count. So here the last line is the way to get the count, obtain the count. So let's think about what the result probability distribution should be. As I said, I didn't set the parameter value shot, so I'm just using the default value, 1024. So what you can imagine is I prepare the circuit, I measure it. So it was a 0, and then we apply the X gate, and it's gonna be in some state, we measure it. Then the result would be 0 or 1. And whatever it is, it's gonna be collapsed into that state. We make another same circuit and we measure it. do the repeatedly 1024 times, then the output should be again for the single qubit 0, there would be only 0 and 1. And based on how many times we get 0, how many times we get 1, we can make a probability distribution. So here, the qubit is prepared in 0 state initially, and then we apply X gate. So let's think about what the output should be. And pass this result count into the function called plot histogram. We can, sorry. We will see the result. In this case, we're gonna get output state 1 with 100% probability. And we can also print out this count. So if you print out instead of plotting, this count result has a dictionary data form. I guess you guys learned the dictionary. So as I said, it can be either 0 or 1. And for this case, we get only 1. So getting state 1, and then we use the shot number 1024. So out of 1024, all 1024 times we measure this state as 1. That's what it means. And as I said, if we know how gate works on each basis, we will know how this gate works on general situation. So, and we just checked how X gate works on 0 state, which showed X gate transforms 0 to 1. And let's check how X gate works on the state 1. So again,
could I ask a couple questions that I'm seeing in the chat from for the block that we just ran for running the previous circuit? So some of the students wanted to know what exactly does backend mean again, if you could repeat that, and also what exactly do the counts mean here?
Okay. So backend is where we run the circuit on. So we can run the circuit on the simulator or quantum computer. And here we are just using simulator. And this particular simulator name is a QxQ simulator. So the backend can be, so that, let's see. Here, backend is whatever we run the circuits on. So it can be simulator or quantum computer. And since there are more than one simulator, which is in the package called AIR, we use the method called, we use the get backend method and select this particular simulator that we want. And we define it as a backend because, and then that means we're gonna run circuit on the simulator. Does that make sense?
Yep. And then also counts.
Count, yeah. So as I said, I think it would be easier to see in the Hadamard gate. Well, let's just go to the Hadamard gate to understand the count concept more clearly. So here is the circuit, 1 qubit circuit. And here we apply Hadamard gate. Again, the qubit state is initially prepared in a 0 state, and we apply Hadamard. And through this command, we measure and store in the zeros classical bit. And this is the circuit. And we execute this circuit again on the backend, which is a simulator for now. So we run this circuit on the backend and ask it, after run it, give me the result, which is, sorry. So if you remember, what Hadamard does is Hadamard transforms 0 state to a uniformly superposition state called plus state. So if you see the expression, the superposition state is a linear combination of 0 and 1 state. And again, when we measure it, it's gonna be either 0 or 1. And for plus state, just like a fair coin, if you flip the coin, you're gonna get sometimes head and sometimes tail. If it's a fair coin, most likely 50-50 times, 50-50 probability you're gonna get zero head or tail. So it's basically the same thing. Instead of toss several times, you measure circuit that many times. And see, the first time you measure it, what did I get, 0 or 1? Second time you measure it, what did I get, 0 or 1? And what we expect, since we already know the state, what we expect as a result should be 0 and 1 with a 50-50 probability. But as just like a coin, even if the head and tail should show up 50-50 probability, if you just toss 5 times, sometimes you get 4 times head, 1 times tail, even though we expect half and half. But if you toss so many times, it will close to be 50-50, like a I don't know, like a millions of times, and 500,000 would be head, 500,000 would be tail. So when you increase the number of toss, you are gonna be closer and closer to the ideal probability. Same thing, this number of toss is number of shot is similar to number of toss. So if you set the shot parameter really small number, even though it's supposed to give us 0 and 1 as an output with half and half probability, it's not going to be exactly half and half. So for example, let's see, when we execute in the shot parameter, let's do 2. Yeah, even if it's a 0 and 1, half and half, when I do the only 2 times shot, happen to give me both state 1. Just like when we threw the coin only 2 times, and I happen to get head both times. And then instead of 1,024, let's do 100,000. Then it's getting very close to 50-50. So again, count shows so this is from the count, you can convert it just the probability and then plot it. So out of 100,000, like this many times I measured state 0, this many times I measured state 1. Then you can divide each count by total count, which will give you a probability. That's what the plot histogram does. They convert from count to the probability and show you the result as a plot instead of this dictionary form. Does that make sense?
Yep, and I think one question that I'm getting in the chat is there some kind of optimal number of counts that you have to, shots that you have to use, or the more you use, the better?
Well, more you use, the better. But yeah, I mean, just like tossing coin, if you increase the number of shot really, really high, then it's gonna give you more and more ideal answer. But 1,024, you kind of see what it should be. If there is always, error from the finite number of shot. So yeah, if you want to get really, really ideal answer, you might want to increase number of shot as many as you want. But 1,024, or like about most of the time, if you have like a couple thousand times, you kind of get fairly close to the ideal answer. Then you would know what is the result that you would expect for this computation from the ideal quantum computer.
Okay, and another question is about this. So in the block that is just below this one, there is this line that says QC.barrier, and so when the students wanted to know what that's doing.
Okay. Okay, well, let's go back to the XGate since that's what we were doing. And then I was about to do how XGate works on the state 1, which also has a barrier here. So again, here we need 1 qubit, 1 classical bit. This number is a number of a qubit, number of a classical bit. And then, but now we want to apply XGate to the state 1. But again, qubit is always prepared in 0 state initially. So first we have to do something so that qubit is prepared in one state before we apply this X gate. And we know how to set the qubit in a one state when it is a zero, state is zero initially. We need to apply X. Then initially zero state will be in the one state. And then now qubit is in one state, and then we apply X gate, which will tell us what's gonna be the result when we apply X gate on a state one. Here I put the barrier just to, it doesn't do anything. I just put it here so I can visually separate the input state. So I'm just saying before this barrier, this is the qubit is an input state. It's prepared in the input state that I want. And then I'm gonna apply this gate on this prepared input state, which is 1 for this case. And after we do the operation, again, this is 0 is the index of the qubit, which is 0, 0's qubit, apply X to the 0's qubit, measure 0's qubit, and store the measured value in the 0's classical bit. And that's the circuit that we want to execute. We just finished building it. And we run this circuit on the simulator, the backend that we already defined earlier. And again, after running the circuit, get the result, basically count. And think about what we should get. For this case, we know X gate should transform state 1 to 0. So I'm expecting 0 with 100% probability. And it does. Another thing we can notice from this circuit is this circuit contains 2 X gate. And then it was initially in the qubit was initially in the zero state, state 0. And after we execute this circuit, after we do this gate operation, output is 0. So that means initially 0, and then applying this operation, which is 2X gate, we got 0, 0, 0. That means this operation by 2X gate didn't do anything. So identity, which means X gate is its own inverse. So we can do similar thing for the Hadamard gate. We can define quantum circuit with 1 qubit, 1 classical bit. And then we want to know how Hadamard works on the state 0. And since the qubit is already prepared in the 0, we don't have to do anything. Just apply Hadamard on the 0th state. Measure the 0th qubit and store the value on the 0th classical bit. So we built the circuit. We can check graphically using the draw method. And execute this circuit on the backend again. You can use a default shot or many shots. And plot the histogram. And as we already saw, for this state, we got the 0 and 1 state as an output with a 50-50 probability. And now we want to know how Hadamard works on the state 1. So again, we build a circuit with, we just need 1 qubit for this case and 1 classical bit. And again, to prepare the qubit in the state 1, we need to apply X gate on that qubit. Then now it's in the state 1. That's what we want as the input state. I put the barrier to say, at this point, it's going to be in the state 1 as we want as an input state. And then apply Hadamard and measure it and draw it to check. Execute the circuit on the simulator. The backend is a simulator for now, and then obtain the counts. And what we see here is again 0 and 1, 50-50. Because as we know, the Hadamard should transform state 1 to the minus state, and which is 0 minus 1, another uniformly superposed state, uniform superposition state, which has the same magnitude coefficient, meaning then half and half probability. So that's what we get. So well, we got what we expect. This last circuit is to check if Hadamard is its own inverse. Again, we need a quantum circuit with 1 qubit and 1 classical bit. And you can prepare a qubit in the 0 state or 1 state, whatever you want. But what we need to do after that is just apply Hadamard gate 2 times. If it's its own inverse, then together works as an identity. That means when we get output, it should be same state as the input state. So here, I'm just applying these 2 Hadamard gate on the state 0. Then if Hadamard is its own inverse, then my output of this circuit should be 0. So let's check it by running the circuit on the simulator. And it's 0. Okay, let's prepare the input state as state 1. Prepare a qubit in the state 1. Then after this X gate, qubit will be in the state 1, and then I apply 2 Hadamard. Then if Hadamard is its own inverse, what I should get is state 1 with 100% probability, which it is. So Hadamard is its own inverse. Now let's move to the last important single qubit gate.
And Hwajung, we'll take our break after this, right?
Yeah, it's kind of going slower than I thought. So.
That's okay. If we don't get through everything, that's no problem. It's better to go through it well.
Okay. So the last important single qubit gate is called the phase gate. So as we learned, the qubit state is a complex, two-dimensional complex vector, meaning that coefficients for each basis is a complex number. And as you know, complex number has magnitude and phase. So if we factor pull out the common phase, which is called the global phase, then we can represent this arbitrary state psi as the expression shown in the slide. After factoring out the global phase, the remaining phase in the parentheses is called relative phase. So this phase gate might be a bit more confusing than previous 2 gates. Global phase is not measurable, but relative phase is. So this last important single qubit gate, phase gates are the operation which impose this relative phase on a qubit. That's what it does. So first phase gate called Z gate. Z gate is one of the phase gate, and it corresponds to pi rotation around the z-axis. Again, all the operation, unitary operation, quantum gate is a rotation. The circuit diagram shows how Z-gate works on each basis. So Z-gate doesn't do anything for basis 0, but it imposes phase pi on the state 1. Since e to the I pi is -1, if you see the column vector notation, Z-gate transforms 0, 1 to 0, -1. To detect the impact of the phase gate, what phase gate does, we need to apply this phase gate onto a state which is not the basis gate, since basis gate are on the rotation axis. We're talking about rotation around the z-axis, and we want to see some differences before and after the transformation. By this transformation, then we want to apply this transformation on the vector, which is not on the rotation axis. So let's think about the plus gate we learned as a uniform superposition state, which is illustrated in the Bloch sphere. And it is a gray vector, which is the plus state. And then we apply Z-gate on it. That means we rotate this vector around the z-axis by pi. Then gray vector will become purple vector, which is minus a state. So which you can easily see from the Bloch sphere description. That means Z-gate transforms plus state to minus state. You can also check, using math, using the linearity property of the gate, this transformation. So if you see the expression, I apply z to the plus state, and plus state is 0 plus 1, and with multiplied by normalization coefficient. And again, it's a linear operation. So z applies 0, z applies 1 separately, and we combine it. E to the I pi is -1. So if you follow the math, then you will arrive on minus state. So what we just like what we confirmed from the figure, Z gate transforms plus state to the minus state by imposing phase pi, relative phase pi. And again, relative phase is remaining phase in the expression. So if you see the expression in the middle, you see that Z gate impose phase pi. Phase gate S works similarly to the Z gate, except it rotates pi over 2 instead of pi around the Z axis. So if you see the mathematical expression, how S gate works, S gate impose the phase pi over 2, relative phase pi over 2 instead of pi. That's the only difference, but also it rotates around the Z axis. So in the block sphere figure, this gray vector will transform to the purple vector instead of the purple vector, which is pi over 2 from the plus state.
If I could just jump in with a quick question. Actually, maybe you're just going to talk about it. So my question is not useful, but some of the students were asking when would we use these phase gates in circuits, and like what do they give us? So maybe I guess you're just going to talk about that now.
Yeah, I was about I just was about to talk about it. So now that we know that qubit can be in the superposition state, and we just learned something called relative phase, which can be used as another resource to encode information. What we can do is we can perform computation among the terms in the superposition by interfering them, where the output is determined by this relative phase. So let's see the top circuit. So we can set the qubit in a state plus a state by the Hadamard gate. Then the phase gate will encode the relative phase. Then by the last another Hadamard gate interfere the two terms and result the output. It's probably not easy to understand, but I'm gonna go through several slides, so just bear with me. And then the second circuit in the bottom is a specific case when the phase gate is the Z gate, which impose 0 phase to the state 0 and phase pi to the state 1. So after going through the Z gate, this superposition state 0 plus 1 will become 0 minus 1, since e to the I pi is -1. And then applying the last Hadamard gate at the end of the circuit, what happens is, since we know Hadamard transforms 0 to 0 plus 1, 1 to 0 minus 1, as written in that expression. And if you see that expression, you see that 0 state gets canceled and state 1 gets amplified. And then the final output would be 1. So that's the interference. And this canceling and amplifying, of course, will be determined by the relative phase we impose on the qubit state by using this phase gate. So here the bottom figure describes this interference process of the circuit. So if you see the bottom figure, which corresponds to the top circuit figure, the first Hadamard is used to create two computational paths. And then phase gates works parallelly on this computational path, impose the relative phase. Then we apply another gate to reverse the process so that the two computational paths become one. And for that purpose, we applied Hadamard gate here, because Hadamard is its own inverse. And then now we are gonna go to the Jupyter notebook to build a circuit with this phase gate. Any
How
questions?
about we do a break and
Oh, yeah.
then we can jump into the Jupyter notebooks after that.
Sounds good.
How's that sound? Okay, cool. We'll do just a slightly shorter break. If folks want to come back, we'll do like 7 minutes or so. So come back at 22 after the hour. I'll post that in the chat. And then we'll pull back up our IBM Quantum Experience accounts. Cool.
Okay. Yeah.
All right, we'll be back in a few. All right, hopefully folks had a great break. We will get started again. And like I said at the beginning, please remember Akshay has prepared an incredible lab that will go through all of this again, and you'll practice with your homework. So lots of practice to come. All right,
Okay.
Hwa-Jung, back to you.
Okay. So we're gonna skip making a quantum circuit with a phase gate. Since you guys are gonna do that in the lab, we are gonna move to the composite system. So composite system is a system with more than one qubit. So of course, the simplest composite system is a 2-qubit system. So we're gonna focus on 2-qubit system. The state of a 2-qubit system is normalized vector in 4-dimensional complex vector space. So there are 4 basis vectors. And just like for 1 qubit, which is a 2-dimensional complex vector, we get the two bases from the one classical bit state. One classical bit has a 2 states, 0 and 1, and that was the basis vector for single qubit state. So just like that, this basis vector for 2 qubit states are from the 2 classical bit possible states, which are 0, 0, 0, 1, 1, 0, 1, 1, and which is represented as a shorthand notation, and also can be represented as a 4-dimensional column vector, as is shown here. The state of a 2 qubit is transformed through unitary operation, called the quantum gate, also called the quantum gate. To build a quantum circuit for the 2-qubit system, we need 2 wires now. And this can be a bit confusing, but so the bottom wire is, so you see the quantum circuit in the slide. Bottom wire is corresponding to the most significant bit. Top wire corresponds to the least significant bit. So when you read encoded bits in the qubit, you read from bottom to top. Then any single qubit gates can be applied for each qubit. Then the output state after this operation is called a product state, meaning that it can be factorized. As the diagram and the mathematical expression shows, for this particular case, the output state will be, as I said, read from bottom to top, gamma alpha 0, 0 plus gamma beta 0, 1 plus delta alpha 1, 0, delta beta 1, 1. Since it's a product state, it can be also represented as a tensor product of the 2 single qubit gate, tensor product of the 2 single qubit states. So we're not going to go into detail about tensor product, but you can kind of see the rough idea what it is from here. So the information on the 2 qubit system can be manipulated through 2 qubit gate, not only several single qubit gates, which we did in the previous slide. And here I introduce the most important 2 qubit gate called CNOT, stands for controlled NOT or controlled X gate, since X gate is a NOT gate. And the diagram shows here shows how CNOT works. So CNOT takes one of the qubit as a control, the other as a target. Here the plus in the circle symbol is addition modulo 2. I don't know if everybody knows addition modulo 2. Here we can see in the middle of the slide, you see how this CNOT works for each basis. There are 4 bases, 0, 0, 0, 1, 1, 0, 1, 1. When each basis is an input, what would be the output after applying CNOT gate? So in this particular example, I took the bottom qubit as control, top qubit as a target. And if the input is a 0, 0, means the control is in a 0 state, target is a 0 state. After applying CNOT, the output state will be, again, read from bottom to top, 0, 0. because the CNOT leaves control qubit states alone. It doesn't change. So the bottom qubit will be 0, and the top qubit only gets flipped if the control qubit is in the state 1. Since the control qubit for this case is not 1, so it doesn't flip the state B. So 0, 0 becomes 0, 0. And 0, 1 becomes, then again, read from the bottom to top. The bottom qubit will stay same, 0, and the top qubit will not be flipped since the control is not 1. Control is 0, so 0, 1 becomes 0, 1. The next one is 1, 0. Again, read from bottom to top. In that case, control is 1, which will remain 1 after CNOT gate. The target will be flipped because in this case, control is 1. So 1, 0 goes to 1, 1. The last basis, 1, 1 also goes to 1, 0. So that's how CNOT works. CNOT gate works for 4 bases. Since we know how this gate works on each basis, we'll figure out what would be the outcome when the control qubit is in the plus state and target is in the 0 state. So you can try to go through some simple algebra, and let's think about for a second. So we're going to go through step by step. So the expression left side of the equation says, apply CNOT gate on the state AB. And now I said A state is in the plus state, which is 0 plus 1, multiplied by the normalization factor, 1 over square root 2, and B state is 1. This, before CNOT gates applied, this 2-qubit system is 0, 0 plus 1, 0. Then the quantum gate, as I said, is a linear operation, so it works linearly for each state. And we just went through how each basis state transformed through CNOT gate. So 0, 0 will become 0, 0, 1, 0 will become 1, 1. So the output state is 0, 0 plus 1, 1 times normalization factor. It is maximally entangled state called Bell state. This maximally entangled state cannot be factorized, unlike product state that we saw in the previous slide. So I think a lot of you probably would have heard the terminology entanglement. So entanglement is non-classical correlation between quantum systems. So when you measure one of the qubit in the Bell state, which has 2 qubits, if you measure one of them, then the other qubit automatically set into the same qubit state, meaning that they are correlated. But this quantum correlation is very different from classical correlation in the sense that the state of those qubits are not determined at all before the measurement. So like a superposition, entanglement is a key resource for quantum computation. Entangled state can be utilized as a medium to perform computational tasks, which is not possible for classical systems, like for teleportation or superdense coding. So here the diagram shows how we make a Bell state, how we build the Bell state circuit. So top left side diagram is what we just went through. So we know if we apply CNOT gate, having putting control qubit in a superposition and target qubit is 0, we know that the output state will be Bell state. To make the circuit for that, as we know, the qubits are all of the qubits are prepared in a 0 state initially. So put the bottom qubit, control qubit in the plus state. We need to apply Hadamard gate on the control qubit, and then apply CNOT gate, having plus state as a control qubit, the other one as a target. Then the output state of executing this circuit, but then after executing this circuit, this 2-qubit system will be in the Bell state. The bottom diagram shows the circuit for quantum teleportation. which uses this bell pair as a way to teleport the state. So in the circuit, top two qubits are bell pair, as you can see from the Hadamard and CNAC gate applied on the top two qubit. And then if you measure one of these bell pair with the bottom qubit in the particular way, then what happens is this state of the bottom qubit will transport to the top qubit. So to do that, we need the bell state is used as a tool. So now we'll go back to the Jupyter notebook. We're done with the slide. And we skip the phase gate. We're gonna make a bell state circuit. So now we move to the 2-qubit system. So when we define the quantum circuit, we need to pass 2 and 2. The first number is for the number of qubit, which is 2. And we want to measure both of them. So we need 2 classical bits. Apply Hadamard gate to the first qubit. Again, the index starts from 0. So the top qubit is 0th qubit. Next one is first qubit. So here, 1 is the index of the qubit. So apply Hadamard on the first qubit, and then apply CNAC gate, having this first qubit as a control, 0th qubit as a target. And then measure it. And the argument here is, first list is the index of the qubit that we are going to measure. We want to measure. And the second argument, list of the index of the classical bit where we are going to store the measured states on. So measure 0th qubit, store on the 0th classical bit, measure first qubit, store on the first classical bit, and then draw to check the circuit. Can I keep going?
Maybe I could jump in with a couple of questions from the chat. So people were asking about, so if you scroll up to the code for the circuit, people were just wanting to clarify again about the 1, 0 and the CX. What do the numbers mean there? And also then with the 2, 2, so does that just mean 2 qubits and 2 classical bits?
Yeah, so here, top number 2 and 2, here is the number of qubit and number of classical bit. Rest of the numbers besides them is the index. So here we need 2 qubit. So first one is a 2 qubit, second one is a 2 classical bit. That's what we need to make bell state circuit. And then we tell them apply Hadamard gate, but we have 2 qubit. So which one should we apply Hadamard gate on? So I say apply Hadamard gate on the first qubit. It's like a name. The top qubit has a name 0th qubit. The bottom qubit is first qubit. So I say apply Hadamard gate on the first qubit, and then apply CNAC gate. But then what you, oh yeah, I didn't. So what you pass on the CNAC gate, as we know, CNAC gate needs target control and target qubit. And then I say this number is the index of the qubit. The first argument of the CNAC gate is a control. Second argument is a target. So what I'm saying is apply CNAC gate. When you apply it, first qubit will be the control, and then 0th qubit will be the target. Since we know that the plus state should be the control, and I apply Hadamard gate on the first qubit, so that will be my control to produce bell state. And then we measure it. I guess that was clear for the measurement part.
Yeah, so one of the students was asking that it looks like in the measure, it looks like that you're measuring like the same qubit twice. So people want to clarify is that what's going on, or is there something else that's going on in that measure statement?
So just like a single qubit case, when we when we made a single qubit circuit, when we measure it, there were two arguments. The first argument was the index of the qubit that we are going to measure. Second one is the index of the classical bit where we are going to store the measured state on. So the first argument is the index of the qubit. Second argument is the index of the classical bit. But now we have more than one qubit. When you pass the argument, we pass the index of the qubits that we are going to measure in the list form. So we measure zeroth qubit and first qubit. We don't measure same qubit twice. It says measure zeroth qubit and measure first qubit. And the second argument of the this method is the classical bit index. After you measure it, where are you going to store the answer to? What each qubit measured state goes to where is based on based on the order of the index in the list. So zeroth qubit measurement value goes to zeroth classical bit. First qubit measurement value goes to first classical bit. So again, the first argument is the index of the qubits they want to measure. We're measuring both qubit, zeroth qubit, first qubit. And the second argument is the index of the classical bit, where each qubit, each measured value will be stored at. So after we draw, you can see the diagram for the circuit. So as we program, Hadamard is applied on the first qubit. CNOT is applied having first qubit as a control, zeroth qubit as a target. And after you measure zeroth qubit, store on the zeroth classical bit. After you measure first qubit, store at the first classical bit. So that's what for example, quantum computer or simulator should execute, this the instruction, what they have to do. And so they execute the Bell circuit on the back end, where now it's a simulator. After running the job, get the count, and we see the result. And as we expected, only the output state, which has the same value for both qubits, are detected as half and half probability. So far we kept using only the simulator, and finally, let's try to use real quantum computer. So we're going to execute this Bell state circuit on a real quantum computer. So first, let's overview all the quantum computer options that we have. So if you go to this icon looking chip looking icon and open this on the new tab, don't just click it, then it's gonna close the Jupyter notebook. Then, oh man, I guess it takes a time to load. So what this page should show is all. So there are two tabs, all tab and yours tab. This all tab will show the all deployed IBM quantum computers, including that you can access and you cannot access. Yours will show the all possible IBM quantum computer that you can access. Since it doesn't seem to load fast enough. Okay, whenever it loads, we're gonna go back. So to access the quantum computer, IBM quantum computer, first we need to load account and define the provider. But if you work in IBM Quantum Experience, IQx, this pre-coded cell already did that for you. It already coded load account and then define the provider. So after you do it, you're under your account and you got your provider. Then you can list the backend of this provider, meaning that provider has several backend, just like Air has a several simulator as a backend. Your provider has several backends that you can access, and you can list them in this Jupyter notebook by running this command, provider.backend parentheses. Then, as you see, there are multiple backends. The first one is a cloud simulator, which is not a real quantum computer, and rest of them are real quantum system. Let's see if it's loaded. So among this, you can pick one of them.
One quick question I'm seeing from the chat, this is kind of a fun question, is does the name of the computer refer to where it's located?
No, it's not, but it's name of the computer is from, I heard the city name, but it's not where it's, I heard that like the first few computer has a name where it's located at, but later it's not really corresponding where they are, but just a city name. So let's see, I wanted to show the page, but it's not really loading. Okay. So among this accessible quantum system, you can pick one of them where you're gonna run your circuit. So here I picked IBM Q Athens. And just like how we grabbed the chasm simulator from Air package, same way, instead of Air, here I say provide. Here we say provider, and using the method get backend, get me this particular IBM quantum computer. After we set the backend, we can. So since even the page is not loading, I don't know if we can do this. So now we can execute the circuit on this chosen quantum computer using through the function execute, passing the Bell circuit that we just built, and then passing the backend we just defined, we just chose. And then here are the shot parameter for simulator. You can increase the number of shots as many as you want, but for real quantum computer, real quantum system, there's a limit. The number of max shot is 8192. And again, as you increase the shot number, then the distribution will be more accurate. So I set the shot parameter as a max shot, and then run the cell. Once you run the cell, so for simulator, once you run, when you execute circuit on the simulator, the result gets returned instantaneously. But for real quantum computer, that's not the case. So once you say, run my circuit on this backend, then what happens is this job is positioned in a queue on particular backend that you select. So we kind of briefly saw at the very beginning. I don't know if this page will load. Oh yeah, let's this one load. So if you go to this dashboard page and see the right side of the page window, then you see each system has queue information. You can see the queue information for each system. So here, you guys probably don't have Manhattan, for example, let's see, San Diego. So San Diego, here is some simple information. It has a 5 qubit and quantum volume 32, and has this many jobs are waiting. So if the queue is so long, then probably you're not gonna get your result soon. You're gonna probably have to wait for a while. Also, this quantum volume, a lot of system has a quantum volume information. This quantum volume is basically a metric to show the computational capability. So higher number, the better. Usually a higher number, higher quantum volume machines are have more jobs in the queue, of course. So if you don't have enough time to wait, you might want to consider this queue information when you choose your backend, your quantum computer. So after you run this cell, then, as I said, it's going to be positioned in the queue. and you want to know the status of your job. Is it still waiting? Is it completed? And those information, your status of the job information, you can check on this job page, which is also icon, one of the icon on the left side of the window. And if you open it, here's a job page. Because a lot of people are on the cloud right now, so it takes kind of time to load. So what information this page has is each line is each jobs that you ever submitted to the IBM quantum system through IBM quantum system. And then first column shows the status. For example, completed, pending, validating, etc. And then when it was created, and each job has its ID. So it has its job ID. And service is the one showing which quantum computer you chose for this job, where this job is running, what quantum computer this job is running on. So whenever this status is completed, then the cell will stop running. So once again, getting the result from quantum computer takes so long time. So you don't want to run same circuit again once you get the result that you wanted. And you can use, for example, for me, I already ran this circuit on this IBM Q Athens machine, and I want to show you the result. I don't have to run this again, but what I can do is this backend that I chose, I can retrieve the job that I already ran, passing the job ID, which I can grab from this job page, and you can see what is the ID of the job that you want to retrieve. And then you assign that to job variable. Then from that job that I retrieved, I can get the result and get the count. And this is the result when I execute the bell circuit in that machine. So as you see, we are expecting only 0, 0, and 1, 1 as an outcome, but you see there's a small probability detecting 0, 1, and 1, 0, which is different from the simulator result. I ran that same circuit on different computer, IBM quantum computer earlier, so I can retrieve that old job from that particular backend. And if you see the result of executing the circuit on that IBM QxQ machine, this is the result, which is also different from the simulator and different from the other machine's result. So, only 10 minutes. So the reason for this discrepancy comes from the fact that the current quantum system and near-term quantum system have noisy qubits and noisy gates and noisy measurement. So what we get as an output from simulator is the result from ideal quantum computer, which doesn't have any noise. And this noisy property is different based depending on the devices and even on individual qubits, like depending on device, just like what we saw from this result. So one of the most important research area in quantum computing is to investing the way to reduce this noise or reduce this noise to improve the result. So people are, of course, developing better hardware and try to find a way to mitigate error, optimizing circuit, and come up with a more suitable algorithm can work better on this noisy quantum computer to utilize this quantum computer power for the computation. So with this Bell circuit execution, I hope that you get some flavor how to running the circuit on real quantum computer. And I think this is all I prepared. So before I end today's session, I'm gonna show some opportunity that you can be engaged to be more active in the quantum computing community. So there is a program called QxQ Advocate. And QxQ Advocate program is a program to support people who actively contribute to the QxQ community. If you become QxQ Advocate, you can apply mentorship program, working on 3-month project together with a mentor who are IBM quantum researcher or educator. And also advocates will be added to the group of quantum experts and will be part of the regular information sharing session. Advocate will receive special access to core member of the QxQ team for asking questions and talking about idea. Also, there are a lot of quantum computing community events throughout the year. And if you're active QxQ Advocate, you will be invited to attend those events. So you can apply this program. An application will be open in June. So you can go to this website to fill up some information, then you will be notified when the application opens. Then after you apply the program, then you need to pass a test, some tests. If you see the test, each question, there is also information what you need to study with the website linked. So if you know some basic, while you are taking a test, you can study as it says. So it wouldn't be too bad. So after you pass the test and then being involved, and here is the list of the idea how you can be involved. So making open source contribution in the QxQ GitHub, organize a QxQ event, and help try to answer to a question in Slack or Stack Exchange, or write a paper or blog using QxQ. So this is an opportunity that I want to introduce before I finish today's session. And that's it for now. So I hope that everybody enjoys and hope to see you guys in another QxQ session in the future. That's it.
Hwa-Jung, thank you so much for the excellent lecture. Would you mind telling us a little bit more about your job and your journey to IBM? There are a few people asking in the chat, just they're curious to know more about you and your work at IBM.
So as I said, I started working from last year, June. So it's not like I've been here for so long time. My background is not really quantum computing at all. So I got PhD for physics, but I was working on galaxy data, so which is totally opposite to quantum. It's a large scale structure, which I got PhD like over 10 years ago. And then I had a couple postdoc, but I kind of stopped my career once I become mom. So I was a stay-at-home mom for 6 years. And once my kids started the kindergarten, I started looking for a career opportunity. And then I got to know about the quantum this quantum computer thing. And like there are so many like learning material. So I kind of did a self-study. There are like videos, lecture, and like including there's a lot of material also in the IBM quiz kit as well, like include reading material, hands-on example. So after did some studying, and yeah, I mean, I probably had a bit easier time than other people who doesn't have a physics background. So after I did some studying, I thought I could do some work in education team. And I had some idea what I want to do, because when I was doing the self-studying, while I could find a lot of material to learn like this theory and running simulation kind of thing, but then when I tried to use actual real quantum computer, I had a lot of trouble finding proper like guide or like information, because like there's more thing to know besides what usual quantum computing textbook teaches if you want to actually running your circuit on the real quantum computer. Because like I said, this is not really fault tolerant computer. It has noise and everything. So when I was studying, I thought maybe it would be nice if there is a material which has information of all these things together instead of I go through like hunt around. So I got interviewed and I made some sample lab example and proposed that I want to make this kind of education material, which is a hands-on example, and which includes not only like making the simulation circuit, but after you do it and you're actually running on the real hardware and go through kind of steps that you might want to know when you do it. So, and then the team liked the idea and then I got hired. And then the last year I kept working on making this lab stuff, quantum computing lab material, which got merged early January this year as a chapter 7 in the QxQ textbook. So it has 7 chapters. And when I make the lab, I try to make half of them as like hands-on, just an exercise using simulator. But the question itself, I try to make it a bit more advanced than usual exercise people usually run into. But then the other half is like running the circuit you made for the problem on the real quantum hardware, the IBM quantum system, including all the information and link for the for example tutorial or user guide for just using quantum computer, like how, for example, what is the transpiler thing, like there is a step the circuit needs to be transpiled before you run the circuit, and then what do you mean like you are going to get not very accurate answer because of the circuit is too long, like kind of things, like a circuit depth kind of thing. And so try to explain those stuff and then make a material so people can use to experience running circuits on real hardware. So try to focus on those running real circuit on the real hardware, since I thought like there's no point of studying quantum computing without using actual quantum computer. So that has been my focus. And yeah, I guess that's it. And then this year starts and I got to give a lecture to you guys. So gotta keep learning because I'm also the basically beginner. I'm not a quantum information expert. So while I'm working, I am learning at the same time.
We're all learning together, right? How about we end with Hwajung, what is your favorite thing about QxQ? And then we can end there.
Favorite thing about QxQ? Well, it's not fair for me to say QxQ is better than, there are other software, right? To code, to program quantum computer, but I actually don't have experience for other software, so I cannot really say QxQ is the best because I never compared. But I'm pretty happy with QxQ because I think the command makes kind of sense. What it does, it's not so hard to follow, I think. Yeah, and then all this graphical notation kind of thing. I mean, I don't know. It's really good to good to use to learn. You know, like through the hands-on example. So when I started studying, I at first, of course, read and write and like a calculation with math and everything. But then it was really helpful once I start coding with the QxQ and do the hands-on example. It feels a lot more intuitive. So I kind of enjoyed it. So yeah.
So it's perfect for all of us who are learning.
Yeah,
Perfect.
it's good to use for learning for sure. Yeah. And if you're advanced, you can contribute by developing. If you're very good at programming, that's another level of learning. That's another, I guess, fun to experience.
All right. Well, thank you again so much for spending so much of your Sunday with us. I hope everyone enjoyed the special event and enjoy your labs this week. We hope to see you at the diversity conference next Saturday, and then we'll be back together again with Fran for lecture next week. All right. Thanks, Hwa Jung.
Thank you for
Have a great day,
inviting me.
everyone.
Yeah, have a good Sunday. Bye.